Jet Propulsion Laboratory has collaborated with Microdexterity Systems Incorporated to develop a new surgical capability. The Robot-Assisted Microsurgery, or RAMS system, developed in this partnership, is a tool that will help surgeons perform operations of the eye, ear, brain, nerves, and blood vessels with unprecedented dexterity. The slave robot part of the RAMS system holds and positions a surgical instrument in 6 degrees of freedom with a relative positioning accuracy of better than 15 microns over a 400 cubic centimeter hemispherical workspace. Commands for the slave robot are entered by the surgeon with an input or master device held like a surgical instrument in the surgeon's hand. Motions in 6 degrees of freedom made by the hand are measured to an accuracy of 25 microns within a 70 cubic centimeter workspace. A demonstration of the removal of a microscopic particle from a simulated eyeball was performed with the RAMS system in 1996. A surgical instrument, mounted on the tip of the slave robot, was inserted into the eyeball under operator control and used to grasp a minute particle and remove it. In 1997, external testing of a prototype of the RAMS telerobotics system was conducted at the Cleveland Clinic Foundation. The RAMS system was found to perform better than manual techniques in 5 of 7 procedures attempted. External tests were also conducted at the Manhattan Veterans Administration Medical Center. To determine the advantages of the RAMS system over manual instrument handling, an experiment was conducted at the University of Southern California School of Medicine to compare manual to telerobotic positioning. Results showed that with sufficient training, significant improvements in precise positioning of surgical instruments are achievable with the RAMS system. A number of new features were added to the RAMS system in 1997. Amplified force feedback and simultaneous slave robot instrument actuation was implemented in an integrated tool sensor design mounted on the slave robot. In the design, a miniature motor is used to drive microforceps on the slave robot, while a force sensor simultaneously measures forces and torques of interaction occurring at the tip of the forceps. The forces measured are scaled up 2 to 5 times and then used to drive the motors of the master arm to give the user an amplified sense of touch. Tool control switches for closing and opening the microforceps on the slave robot were installed on the master handle to allow intuitive operation of the forceps. An index control switch for activating telerobotic control was also installed on the master handle. Upgrades to the real-time computing environment implemented in 1997 include increase in computational power and installation of a hard disk memory storage device for network-independent operation. As a final demonstration of the practical use of the RAMS system, 2 prototype telerobotic systems were used in coordination to perform a microsurgery suturing procedure. 9/0 nylon suture was used to close a 1.5 millimeter long slit made in a thin sheet of latex rubber. 1997 was the 4th and final year of the RAMS development. The technology developed in this effort has been licensed for commercialization to Microdexterity Systems, where an intense effort towards the development of a commercial prototype is underway. A new tool to extend the capabilities of microsurgeons with potential benefits to thousands of patients will become available after completion of clinical trials and certification by the Food and Drug Administration.